Today we're going to look at index laws and negative and fractional indices. And we've got a number of learning goals for today's lesson. We're going to recall and apply the index laws. We're going to recall that any number raised to the power of 0 is 1. We're going to convert expressions with negative indices to positive indices, or using positive indices. I'm not sure what I meant to write there. Convert between surd form and index form as well. So the index laws, if we recall, well, even just recalling what an index is, we've got the base of the index, and then we've got what's called the exponent or the index or the order above. And we can see that there's relationships between these different things. I mean, what this actually, but it pays to actually understand what this means. So this means A times A times A times A m times. M times. Okay, so we're doing it m times, multiplying it out m times. And so it means that if I've got m a's here, and then I multiply by n a's here, that means in total I've got m plus n a's. So that's why this index law works. And it's exactly the same for this one here. If I've got m a's and then I divide by n a's, that means I'm dividing each of these, I'm finding values of a to cancel, because a divided by a is just 1. So each time I find a matching value, a divided by a, for example, if I've got a times a times a times a, and divide that by a times a, I've got, this is a to the power of 4 divided by a squared, then I can cancel one of them, because a divided by a is 1, and cancel another one, and I'm left with 2 on top. So I've got 4 minus 2 left over. So that's why we get the a's, if I've got m divided by a to the n, then I get a to the m minus n being the simplified version of that. That's index laws 1 and 2. For index law 3, if I've got a to the m all to the power of n, that's essentially saying I've got n lots of a to the m, or n multiplying a to the m n times. So it means that I'm multiplying the exponents that I have there. So I end up with a to the m times n. Now for index laws 4 and 5, we can see that if I've got a times b to the power of m, that's the same as having MA's and MB's. And it doesn't matter which order that we multiply them in, because multiplication is commutative. So it means that I can just separate those A's and B's out, and I've got MA's and MB's. So it's the same as having a to the power of m times b to the power of m. And it's the same with the dividing here. Same with dividing if I've got a over b to the power of m. I've got a over b, I've got a times a across the numerator of my combined fraction, and b times b all along the denominator. Now, I've gone through those very quickly. If you need a more in-depth recap, you can go back to the previous videos on index laws where I've talked about them more in depth. The final thing is the 0 power as well. Anything to the power of 0 is equal to 1. And we can look at that as if we look at a pattern. If I've got 2 times 2 times 2, that's 2 to the power of 3. And then if I've got 2 times 2, that's 2 squared. 2 by itself is 2 to the power of 1. So if we have a look at what is happening each time, going from step to step, I'm dividing by 2 each time, dividing by 2 each time. So if I wanted to go 2 to the power of 0, I'd be doing 2 divided by 2 again, divided by 2, and I'm left with 1. So anything to the power of 0 is 1. This would work if it was 6 times 6 times 6 is 6 cubed, because then you divide by 6 each time. So for a to the power of 0, you divide by a each time, and you're left with that 2 to the power of 0, anything to the power of 0, is equal to 1. Just recalling those index laws very quickly, there was a very brief recap. So I'm not surprised if you are a little bit confused, but as I said, go back over the older videos and you'll be able to get a more in-depth look. Let's have a look at some examples with these now. I'll run through these very quickly. So we've got a here, we've got 3a squared b times 4ab cubed. So we're going to be using index law 1 in this case and combine these values together. The 3 times the 4 is going to be 12. I've got a squared times a, which is a to the power of 2 plus 1, and I've got b to the power of 1 plus 3, because I've got b times b cubed. So then I end up with a cubed b to the power of 4 in a simplified version there, using index law 1. Index law 2 now is going to be used for the next one. So I've got 4x squared y5, and I'm going to express it as a fraction using the divide for the vinculum. 8xy squared. The 8 and 4 simplify to 1 over 2. So I divide the top and the bottom by 4. And so I'm going to be left with a half. Now I've got x2 minus 1, and I've got y5 minus 2. So I'm left with here 1/2 x to the power of 1 is just x, y to the power of 3. Now you can technically write x to the power of 1, but you shouldn't be doing that because it's unnecessary. It's certainly convention to make sure that you have everything as simple and neat as possible, and so leaving anything as anything to the power of 1 is not going to be good communication, clear communication. C, we're going to look at index law 3 here. And the question we've got is 3x squared over 5y squared z, all to the power of 3 here. So it's going to be index laws 3, 4 and 5 actually for this one. So here what we can do is we distribute the cubed to every value inside. That's index law 3. So we get 3 cubed x 2 times 3. Sorry, index law 4 and 5, not index law 3. 5 cubed y 2 times 3 and z cubed. So index law 3 is where I've got the multiplying the powers here. So 3 cubed is 27. That's x to the power of 6. 5 cubed is 125. Y to the power of 6. And z to the power of 3 is our answer there. Making sure that we've simplified everything. 27 over 125. I don't believe there are any common factors there that we can cancel. No, 9, 3, 5, no. Okay, so no, there's no common factors there that we can use to cancel those values. Let's look at D. This one is a lot more complicated. Here we've got 3xy squared to the power of 3 times 4x to the power of 4y squared over 8x squared y. I'm going to initially look for anything that I can simplify straight off the bat. I'm going to look at the 8 here and the 4 here and make this 1 and 4, 1 and 2 rather. I'm going to simplify the y here and make that 1, because that's y2 minus y1. I'm going to simplify the x squared here and remove 2 of those ones, because 2 of those will cancel as well. And that means I'll be left with 3xy squared cubed over 2. And then I can expand out what is relevant in the brackets there. So 3x cubed, y to the 2 times 3 over 2, which is 3x cubed, y to the power of 6 over 2. I'm going to show a different way to approach this one. Rather than doing the cancelling straight up, we can expand out and then use our index laws to simplify. And you can choose which way works best for you. So if we look again at writing that question out, 3xy squared cubed times 4x4y squared over 8x squared y. I'm going to separate out the values. I'm going to have 12 over 8 here, and I'm going to apply the index law to the first part. and get x cubed y squared times 3 times x4 y squared over x squared y, and then combine. I can simplify this now, divide top and the bottom by 4, and I'm left with 3 over 2. So left with 3 over 2 here, and if I combine the x, I've got cubed minus 4, sorry, plus 4 minus 2, and then the y's, I've got 6 plus 2 minus 1. So I'm left with now the 3 over 2 x, 3 plus 4 is 7 minus 2 is 5, and y, 6 plus 2 minus 1 is going to be 7, y to the 7. So you can see before, you can express this in any way you would like. You can express it by having the 3 on 2 at the front times x to the power of 5, y to the power of 7, or you can have it the 3x to the power of 5, y to the power of 7 on the numerator and the 2 on the denominator. It doesn't matter, they're equivalent. Last one, e, 2p to the power of 0 plus 3p all to the power of 0. Anything to the power of 0 is 1, so I can replace anything to the power of 0 with just 1. So I've got 2 plus 1, which is 3. So note that if it's in brackets, that's everything to the power of 0. So that whole thing is 1. That whole part of the expression is 1. So the initial p to the power of 0, that's equal to 1, but there's still the 2 at the front. There's no brackets around it. If there were brackets around the 2p, then that would equal 1, the whole thing. But it doesn't, because it's 2 times p to the 0. Okay? Next, reviewing negative indices. Need to remember, if we want to convert from negative to a positive index or a positive to a negative index, any base to a negative index is going to be the reciprocal of its positive index. So if I have anything to the power of negative whatever, then that's going to be 1 over the power, that same base to the positive power. So if I've got x to the negative 5, that's the same as 1 over x to the positive 5. Similarly, if I have 1 over x to the negative 7, the reciprocal of that is just going to be x to the positive 7. Okay, so we can convert from positive to negative indices by making it the reciprocal and making it the opposite of what it was, positive or negative. Some examples using these positive indices now. Looking at a here, we've got 5 over x to the negative 3. This is the same as 5 times x to the 3. We've made it reciprocal, moved it from the denominator to the top, okay, and made it a positive index. B here, we've got 3a squared over a to the power of 5 cubed. A couple of different ways of doing this. I'm going to simplify it in the brackets first and get, using index law 2, and get in the brackets 3 times a to the negative 3, because 2 minus 5 is negative 3, all to the power of 3. So I get here now, if I apply the cube, 3 cubed, a to the negative 9, I get here 27, and the a to the positive 9 can go on the bottom now, because we're going from negative, if we're converting from a negative to a positive integer, we find the reciprocal of it. So C, final question here, a much more challenging one that we're going to need to simplify, over r squared n to the negative 4 all cubed, divide by 5 m to the negative 2 n cubed over r all squared. I'm going to distribute the cube and square to what's in the brackets first. 2 cubed, m to the 3 times 3 is 9, over r squared times 3, which is r to the 6, n to the negative 4 is n to the negative 12 multiplying by 3. We do the divide by, do the divide by 5 squared times m to the negative 4 n to the 6 over r squared, and then convert to a multiplication over r6 n to the negative 12 times r squared over 5 squared m to the negative 4 n to the 6. So I'm going to look at combining my values together. So I get 2 cubed, which is 27, over 5 squared, which is 25. And I've got my m's, so I've got m to the 9 minus negative 4. I've got my n's, which are, I've got divide by negative 12. Okay, that's going to be, they're all on the bottom, so I might leave them all on the bottom there and just multiply them together. And then I've got my r's, so I'll do the n's here, n to the negative 12 times, plus negative 4. Yep, because they're both on the bottom there. And then doing the r's, we've got r squared, and then r6 is on the bottom, so I'm going to minus the 6 away. Left with 27 m to the 13 r to the negative 4 over n over 25 n to the negative 12 plus negative 4 is going to be negative 16. So to express as positive indices now, the m is already positive, but the n is not, so it needs to come up the top, and it's going to be positive 16. The r is negative, so it's going to need to go on the bottom. 25 r to the positive 4. So here I've now expressed it as positive indices. Positive indices. I feel like I've done something wrong. It's because I have now all the way back here, I've done n to the power of negative 12, and there's n to the power of 6, and I should have added those together. So negative 12, this should be plus 6, which would make negative 12 plus 6. This is going to be negative 6, so then that becomes positive 6. So that's what I've done there that's wrong, but everything else seems to be legit. Okay. All right, fractional indices can be expressed using roots. So a fractional index, I can have a look at the fraction, and the fraction that it appears, if it's 1 over a value, then that's saying that's the nth root of a. So if I've got a to the 3rd, that is the cube root of a. A to the 4 is the 4th root of a. And remember what the definition of this is. This means that if I've got some value x and I put it to the power of 4, that is going to be equal to a. Then a is going to be equal to, x rather, is going to be equal to the fourth root of a. So you can see a couple more examples here of that. If I can also use index law 3 to expand, index law 3 to expand this out and see that there's a more general case for m over n rather than just 1 over n. And there's a couple of examples here that demonstrate that and that you get the same answer for that. If we're looking at doing some examples here for expressing the following in index form, let's look at 1a first. In index form, square root of 15. That's equal to 15 to the power of 1/2, because what we've got is the square root is, or square root is the second root of 15 in this case. For b, we've got here the square root of 7x to the power of 5. Now this is the same as the square root of 7 times the square root of x to the power of 5. So in this case, the square root is 7 to the power of 1/2. And our x to the power of 5 is also going to be taking the square root. But because we've got the power here, we multiply this power by the half. So we get x to the power of 5 over 2. The 5 comes from the power that's inside underneath the root symbol, and the divide by 2 comes from the fact that it's a square root. So this is 7 to the power of 1/2, x to the power of 5 over 2. Now let's look at 1c. We've got here that 1c is 3 to the 4th root of x to the power of 7. 3 is out the front by itself. It doesn't have any squares or square roots attached to it, so it is chilling by itself there. We've got the 4th root, so that's going to be the fraction, the denominator of our fraction for our fractional index is going to be 4. The numerator is going to be 7 because we're multiplying by 7 over here. So it's going to be 7 over 4. 3 times x to the power of 7 over 4. Now d, we've got 10 root 10. 10 root 10. Now this is the same as 10 to the power of 1 times 10 to the power of 1/2. Now we can use our index laws. We've got the same base, so we're going to do 10 to the power of 1 plus 1/2. So that's the same as 10 to the power of 3 over 2. 10 to the power of 3 over 2. Now if you think about it, we've answered the question. But if you think about it, this is equivalent to, if we go back the other way, this is equivalent to 10 cubed, and it's the square root of 10 cubed. Based on the fact that it's a 2, this indicates that it's a square root, and 3 is on the top, and it goes inside the brackets there. Now, think about that, that makes sense. 10 itself is the square root of 10 squared. 10 is the square root of 10 squared. So if I take 10 squared, 100, take the square root, I get 10. So that means this is equivalent to 10 square root of 10 squared times root 10. Now we know about our rules for simplifying surds. 10 squared, if I've got this square root of 10 squared times square root of 10, that's the same as 10 cubed underneath the square root symbol, which is exactly the same as what we've got here. Okay, so it makes sense that 10 root 10 is the same as 10 to the power of 3 over 2. Let's look at question 2. It says here, express 5 to the power of 2 over 3 in surd form. So I've got the 3 on the denominator. That means it's a cube root. Okay, so the number here, the number that's on the denominator, tells me what kind of a root it is. The number that's inside, the 5 squared, is going to be inside the bracket here, inside the surd. So I've got here that this equals the cube root of 25 or the cube root of 5 squared. The last question is evaluate 27 to the power of negative 1/3 without a calculator. So this is the same as, because it's a negative index, 27 to the power of 1/3. And we know that if I convert that to a cube root, because there's a cube root underneath, 27, cube root of 27 is 3, because 3 times 3 times 3 is 27, and so I get that the answer is 1/3. Just recapping the learning goals for this lesson, we've looked at reviewing the index laws, we've looked at the anything to the power of 0 is 1, we've looked at being able to simplify negative indices and make them positive indices, and we've looked at being able to convert between surd form and fractional indices.